Hi, in this video, I'm going to show you how it is that we're going to determine what types of relationships we have in the data that we collect in this class. So in AP Physics, we're in the business of collecting data. Every day in class, we're going to be collecting and analyzing data. So it's very important for us to start off the year knowing how it is that we're going to identify the types of mathematical relationships that are being expressed in our data. And so we find is that there's really just a few relationships. This is it. You're looking at all six of them. This is what our data is going to look like. All the data when we plot it is going to look like one of these six types of graphs. And so we're just going to take this video to look at what each of these tells us and how we can then use that to come up with a mathematic expression for our data. Sounds scarier than it actually is. Let's just go through it. So one thing to keep in mind is that basically all of the mathematical relations we're ever going to see this year come down to this basic format here. Y is equal to some constant, we'll call it A in this case, times the x variable raised to some exponent, which we'll just call b. And really, the only difference between the different graphs that we were looking at in that previous slide is just what the exponent of b is. All right, so let's just get into it here. So one thing to keep in mind is this, and I cannot emphasize this strongly enough. The universe is really specific about what types of exponents it lets us raise x to. You're going to be using some software this year called LoggerPro, and LoggerPro will just try to model the data the best it can. It will use any exponent that will fit the data the best. But what we have to keep in mind is the universe doesn't play the game that way. The universe is very specific. Lo and behold, these are the only exponents we're ever going to have. We're going to have one or negative one. And keep in mind, an exponent to negative one just means the reciprocal. It's going to raise to the power of 2 or to negative 2 to 1/2, which is the same thing as saying square root, or to the reciprocal of the square root. And that's it. Those are the only relations we're ever going to get. So let's look at this first one here. A proportional relationship is one where it is linear and it starts at the origin and moves upwards from there. So the mathematic expression of this is simply going to be y equals some constant a times x to the 1 power. All right, or we just say y equals a times x. That's all it is. It's as simple as that. Now, notice there's no y-intercept here, no x-intercept, so we don't have to say plus anything. It's just y equals ax. However, we often have what's called a linear relationship, which is a special case of a proportional relationship, in which case I have a y-intercept. So this is what you're used to with math. Y equals mx plus b is what you'd say in math. We're just going to say it's y equals a x to the 1 power plus b, or in other words, y equals ax plus b, with b being the y-intercept here. And if it was a negative value, it just means we have a negative intercept. I think you remember that from math. But there are other kind of relationships we're going to look at. In all honesty, these types of relationships here are not that common. But what is more common is something that looks a little bit like, say, this one here, an inverse relationship. So an inverse relationship, I'm still raising x to the power of 1. However, it's negative 1. It's the reciprocal. So in this case, what we find is that as the value of x gets bigger, the value of y gets smaller. So I get a curve that looks like this. Notice it's not linear. It's got a curve to it. But the exponent is still 1, negative 1 in this case, right? So really what that means is y is equal to some constant a times 1 over x. Or if you prefer, we could just say y equals a over x. Now, we can also have a squared relationship. Now, in a squared relationship, the exponent in this case is 2 rather than 1. So in this case, every time x gets 2 times bigger, this is going to get 2 squared, or 4 times bigger. If x gets 3 times bigger, this gets 3 squared, or 9 times bigger. So I get this type of curve to it. This is a very common relationship that we encounter in physics. Now, an inverse squared relationship is basically the reciprocal of that, right? So you've noticed this looks quite a bit like the other relationship that we had before. It looks a little bit like the inverse relationship, but in this case, it tends to hug the axes a little bit more closely. And so in this case, what we have is y is equal to a constant times x to the negative 2 power, or in other words, let's see if I can get myself out of your way here. I don't know. Can I move myself? I can. Okay, I'm going to move myself over to here. In this case, y equals a over x squared. Now, this one here is one you might not have used much, but we encounter quite a bit in physics, and that is a square root relationship where we're raising x to the power of 1/2. When you're using LoggerPro, it'll be 0.5. Now, LoggerPro will say, like, the software we're going to use will say, like, hey, I think you should raise this to the 0.48 power. And you guys say, no, I don't think it's the 0.48 power. I think what you mean is 0.5 power, because the universe is very specific. So y equals the constant a times x to the 1/2 power X to the 1/2 power is the same thing as saying square root of x. Again, very common relationship encountered in physics. And then look at this one here. This is the reciprocal of that. This is what happens when I raise x to the negative 1/2 power, or to the negative square root, not the negative square root, I'm sorry, the reciprocal of the square root. In which case, it looks a lot like the inverse relationship. Now, how am I going to tell them apart? Well, that's what we're going to talk about next. How is it, once I've plotted the data, that I'm able to come up with a mathematical relationship that doesn't have y, a, and x, but has the actual values of these things? Well, let's just see how we're going to do that. Oh, I forgot. There's also this sometimes happens. I thought there'd be a relationship between the x and y variables, but when I plotted it, I kept changing x, making it bigger and bigger and bigger, but y never varied as a consequence of that. So what that tells me is the value of y was a constant value, a. It never changed, which means that y and x bear no relationship to each other. They have nothing to do with each other. So that does occur sometimes, and you need to recognize it when it does. Okay, how is it that we're going to come up with these equations? Okay, well, let's see if I can figure out how to move myself here. Okay, here we go. We're going to use a technique called linearization. So linearization is a lot easier than it might sound. So basically, it goes like this. You're going to plot your data. You're going to look at the shape of the data distribution and say, that looks like, say, a squared relationship. And then what you're going to do is you're going to make a new column of values where you're raising x to the exponent that you think is being raised to by looking at the data. And then you're going to plot that data. So instead of plotting x against y, I'm doing, say, x squared against y. And then I look at it, and if that linearizes, that tells me yes, I've got it correct. And if it doesn't linearize, then that tells me I need to try a different exponent. And once I have a linear relationship, I can take the slope of that line from the linear relationship, and that slope will then be the a value that we have in our equation. So let's just walk through it so it'll make sense. Probably right now, you're probably like, what are you talking about, Mr. Sampson? Okay, here you go. So I'm going to take this data here. All right, here's my values for x. Here's my corresponding values for y. I'm going to plot them on this graph. All right, so when I plot them on the graph, I get this. Okay, so I'm looking at this, I say, okay, that shape is not linear, it's not a proportional. I think it's probably raised to some exponent. And so I would just simply look at my choices here, and this seems to be the one here. It tends to look a little bit like that. It's starting with a high slope and is starting to taper off closer to zero. I think I have this one here. I didn't write the names of them in here, but this is a square root function. So I think I'm raising x to the 1/2 power, or to the square root. So what I'm going to do then is I'm going to make another column of numbers. I had my x and y. That's what I had before. Now I'm going to make another column, and this column is going to be the square root of x, or x to the 1/2 power, because that's what I thought the relationship was. So then I'm going to take all my x values and take the square root of them. The square root of 0 is 0. The square root of 2 is 1.4. Square root of 4 is 2. Square root of 6 is 2.4, and so on. And now what I'm going to do is I'm going to plot y values. Instead of plotting them against x, I'm going to plot them against square root of x, right? And so, and I notice I put this is supposed to be 1.4, so it should be over this way a little bit. But then when I look at it, you know what I see? I see a straight line. It linearized. All right. So that tells me I was correct. If the data linearizes, then that tells me I was correct in what exponent this was. So I do know what type of relationship is. And now look what I can do. Since this is a straight line, I can simply find the slope of that straight line, which is a pretty easy thing for us to do at this point in our education. So I just say, well, look, okay, slope is always equal to change in y over change in x. And by the way, in physics, we just need to get very used to this. Delta simply means the final minus the initial, right? So final y minus initial y over final x over initial x. So I'm just going to pick a place where I have a nice intersection so I don't have to interpolate very much. So that's equal to 12. So I'm going to say 12 minus 0. Okay, so I went from here to here. So here's my initial, here's my final. 12 minus 0 for y over my final was 2, and my initial was 0. So over 2 minus 0. And that's going to give me a slope of 6. So now that I know what the slope is, that's the value of a in the equation. So I simply, instead of saying y equals a x to the b power, I know that the b power is 1/2, or square root. So I'm going to express it this way. And I know that that slope value was 6. So instead of saying a, I'm going to replace it with 6. Now, by the way, if y was, say, height, and x was time, I'd replace them with that as well. Okay, so that's how we approach linearization of data and determine what type of mathematical relations we have between our variables in AP Physics. We'll be doing this all year. Thanks for watching.